Well, hello and welcome to week 3 of financial engineering. What I'm going to talk about this week is interest and equivalence. And what that means is I'm going to show how different cash flows at different points of time can be equivalent to another number just based on the interest rate. So what we're going to talk about first is computing cash flows and the time value of money, equivalence, and then single payment compound interest formulas, and nominal and effective interest rates. So all of this is going to be extremely important going forward when you do your project justification calculations. Now, some of the objectives we're going to have is I want you to understand the time value of money. So simplistically, would you rather have $1 today or $1 in 1 year? And I think most of you would say you would rather have $1 today because you could just put it in the bank and maybe earn 1% for a year and have a dollar and a penny in a year. But the concept is that you could do something with that money. In addition, you don't know what's going to happen with inflation. You don't know what's going to happen in the future. So you could say, yeah, you would rather have $1 today rather than a dollar in 1 year. Would you rather have $1 today or $1.25 in 1 year? Well, if it's only $1, maybe it doesn't matter. But what if I told you, would you rather have $10,000 today or $12,500 in 1 year? You probably would say maybe the 12,500. I can get 25% more. So that's what we're going to be trying to understand with the time value of money. And then I'm going to discuss simple and compound interest. I'm going to discuss simple interest because you may see it on the FE exam, but the world, every application you're going to do is going to utilize compound interest. So I'm going to introduce you to the concept of simple interest. I think I have a homework problem on it, but I want you to recognize that in the real world is compound interest. And then I'm going to take you through cash flow equivalence and why, if you're indifferent between $10,000 today and $12,500 in 1 year, then they're equivalent if your interest rate is 25%. And we're just going to discuss that. And it's a little bit, initially it's going to be a little bit esoteric, but I think you're going to get it as we spend basically the next 8 weeks doing these kind of problems. And then we're going to solve problems using these single payment compound interest formulas. And then I'm going to show you how to use spreadsheet calculations. The world is Excel. So the world is compound interest, and all of these problems are solved in Excel. So while I may take you through a little bit of the mechanical way to do it algebraically, these problems are all done in Excel, and I'm going to show you some of the techniques that I use every day in Excel. So again, here's the simple comment: $1,000 today or $1,000 in 10 years. Of course, the answer is today. Especially if you're paying attention to what's going on in the economy. Inflation is its highest level in basically the last 40 or 45 years. $10,000 or $1,000 today has much more, is likely to have much more purchasing power than $1,000 in 10 years. And we have no idea what's going to happen in the next 10 years. Now let's talk about cash flows. Cash flows are costs. I can use them as disbursements. They're a negative number. You can think of them as cost of goods sold, the costs on the income statement that we talked about. And then there's receipts. And so costs are a negative number, benefits or receipts are a positive number. And you can think of benefits as revenues, sales, those types of things on a macro scale. But on a smaller scale, we just think about receipts. And the first part of this second bullet point, the second blue bullet point says, because money is more valuable today than in the future. And that's because of what we just talked about. We'd rather have $1,000 today than in 10 years. We need to describe these costs and benefits at the time they occur. So if we're evaluating a project and it generates a net of benefits minus costs of $100 a year, $100 in year 1 is different than $100 in year 4, is different than $100 in year 10. Okay, let's look at two payment options. One is we're going to purchase a new machine for $30,000, and it's going to have O&M. O&M is operating and maintenance costs of $2,000 a year and savings of $10,000 a year. And at the end of the 5th year, we're going to be able to dispose of it for $7,000. So that's what a salvage value is. And we're going to be analyzing this ignoring taxes. We're going to talk about taxes in week 6 or 7. They're very important, but understanding the fundamentals of the mechanics of analyzing a project, we're going to ignore taxes. And so you could think of this $30,000 machine as a car or a truck. And it's going to cost us $2,000 a year to operate. And maybe this truck will allow us to do our job better, and we will save $10,000 a year. And so we'll have a net benefit of $8,000 a year. And then at the end of the 5th year, we anticipate a lot more maintenance expenses. We're just going to sell the truck for $7,000. So we're going to talk about something new right now, a cash flow diagram. And basically a cash flow diagram is exactly what it says. It's a description of how the cash flows fall out relative to time of a project. So if we look at this table up here in the upper left, we see our $30,000 cost of the equipment, the truck, whatever you're purchasing. And it's good to think of cash flows occurring at the end of period. So the concept is there's a beginning of period and end of period. And so today is end of period 0, and we're working in years, but we could be working in months or 6-month periods. But typically you're going to be working in months or years. And then our cash flows, our savings, and our costs are going to incur at the end of periods 1 through 5. So you're not going to be saving $10,000 today. You're going to be saving it over the first year. And when we do initial passes at projects, we typically work in annual periods. When we get finer, when we get finer at looking at a project in more detail, we may do it in monthly periods, because clearly you're going to be saving over time, not just one point in time. And then we see our costs. We see that our salvage value, and this is kind of, if you have the textbook that I suggested, they tend to treat salvage values as negative investments. So here's our investment. So here's our investment of $30,000, and our salvage value, they put it in this cost and salvage value column. Some textbooks put it in the benefits column because the savings are a benefit. What I want to emphasize here is this is our cash flow diagram, and if you're in doubt, draw a cash flow diagram. If you're taking an exam and you're in doubt, draw your cash flow diagram, take a picture of it, upload it into the Excel file you're working on, so that I can get an idea of how you're thinking. And so basically in this diagram, we're drawing our costs as below the line and our benefits, our savings, as above the line. And you can do it reversed as long as you're consistent. I typically do it this way, but the important thing is that you see the gap between periods. And so you can understand that that if you look at this net amount of $8,000, we got $8,000 in year 1, and that's different than $8,000 in year 4. Your savings are more valuable to you in year 1 than they are in year 4. So this is our cash flow diagram, and it's okay if we net them. I think to begin with, drawing everything on the cash flow diagram is nice, but you could net them and just show a green arrow or a different arrow up that is $8,000, $8,000, $8,000, $8,000, and $15,000. But I think it's good for your understanding to actually put in all the detail to begin with. Now let's say we're going to borrow $1,000 at 8% interest, and we're going to pay it off over a 2-year period. And some of the terms of the loan is we're going to pay half of the $5,000, half of the $1,000 or $500 at the end of year 1, and the other half at the end of year 2. So if you look at what's going to happen here, we're going to get $1,000, we're going to borrow it, we're going to get it into our pockets in year 1, 0. In year 1 and 2, we're going to repay $500, but we're going to pay interest as well at the end of year 1 and at the end of year 2. So we pay 8% interest. We've borrowed $1,000 for 1 year. We pay 8% on it. So our total payment at the end of year 1 is $80 interest plus the $500 repayment. So we're going to pay $580. Now for year 2, we only have a balance on the loan of $500. And so we pay 8% on that. Our interest for year 2 is only $40, 8% times 500. So our payment for year 1 is $580. Our payment for year 2 is $540. And this is how these are the cash flows associated with the payment of the loan. Now recognize that all loans are different. And so the interest rate's different, the term is different, whether you pay interest annually, semi-annually, it's all set up in the terms of the loan. So all of the facts are stated right here in this dark blue box about the loan for this particular cash flow diagram. And so the concept here is money has value. You can lease it or rent it. And payments are called interest. And if you put money in a bank, $100 at 5% for one time period, so I didn't say 5% per year, you will receive $100 back plus $5 at the end of that time period. Okay, so let's get into a little bit of where we're headed for this course. We're going to invest P dollars. That's a present value, a present amount, but get used to seeing the term P, and we're going to receive F values, N periods in the future. This says N years, N is going to be periods. And I is the interest rate per period, in this case per year. And so we're going to draw our revenues as positive amounts and our disbursements as negative amounts. So let's talk about simple interest on a loan. And so you're not going to see this in the real world very often. There may be somebody that does simple interest, I'm not sure. But where you will see it is possibly on the FE exam. And so simple interest on a loan is only paid on the amount that you borrowed, the original amount. It does not include interest earned or owed. So if you borrow P for N years, the total interest owed is P times I times N. Now, what this means is you don't owe interest on the interest. If you borrowed $100 at 5% for 2 years, you're only going to owe $10. However, you could owe, if you had compound interest, at the end of the first period, you'd owe $105, and you would owe slightly more if it was not simple interest, if it was compound interest. But this is simple interest, so you do not include interest earned in the calculation. So if we have a loan of $5,000 for 5 years at a simple interest rate of 8%, the total interest we owe is $2,000, and at the end of the loan, we pay a balance of $7,000. Now let's contrast that with compound interest. Compound interest, and this is the real world, this is what we're going to be doing in the real world and all of these examples and in your real life. Interest is computed on the unpaid balance. So that's the principal and any unpaid interest from the preceding period. Any unpaid interest from the preceding period. So if we have compound interest on this same loan that we had in the simple interest example, the total interest that we earn is going to go according to this formula. Interest equals your present amount times 1 plus your interest rate raised to the number of periods power minus your original principal, your present sum of money. So this exponent gets us into the compounding of interest. And instead of earning $10 as we would earn in simple interest, we actually earn $10.25 because the $5 of interest that's earned at the end of year 1 earns 5% as well for the second year. So let's look at an example of borrowing $5,000 at 4% interest. At the end of 1 year, we owe $5,200. At the end of 2 years, it's $5,408. We have $208 of interest. At the end of 3 years, it's $5,600 and $5,624. We have $216 of interest. So $200 of interest, $208 of interest, $260 of interest. I think you can clearly see as the interest rate goes up and as the number of years go up, these differences from simple interest to magnify quite a bit. Simple interest, we would only have $600 as our interest. So for compound interest, if you take this to the limit, this future amount that we're going to have, so going back here, you can back into a present amount with this formula. And the future amount is F equals P times 1 plus I to the n. Now this class is open book, open notes, open world. You don't need to memorize formulas, but this formula here is fundamental to engineering economics and financial engineering. When I first taught this course, I was retiring from Union Oil, and I was talking with one of my friends who was the chief operating officer at Sempra Energy, that's the utility in San Diego. And he asked me what I was going to be doing, and I said, well, I'm going to be teaching engineering economics, financial engineering at Cal Poly San Luis Obispo, and venturing off into doing some consulting. He said, engineering economics, F equals P times 1 plus I to the n. That's all you need to know. And in reality, this is basically, you can almost solve any problem with this formula. Because of Excel, we can build tables. We don't need to go through all the other formulas that you're going to end up learning. Alternatively, you can solve for P, and P equals F over 1 plus I to the n, or P equals F times 1 plus I to the minus n. So which one of these is true? P equals F over 1 plus I to the n. So I'm going to take you through different methods of calculating interest on a loan. So let's say we have a loan of $5,000 for 5 years at 8%, and we're not going to pay anything until the end of the 5th year. Each year, we're going to have a larger and larger amount of interest due, because at the end of the first year, we owe interest on the original $5,000. At the end of the second year, we owe interest on $5,400, which is the original amount we borrowed plus the interest that was earned in the first year. And at the end of the third year, we owe interest of $466, which is interest on the balance at the beginning of this third year. So you can see that this balance grows, and it grows by more than $400 because we're paying interest on the interest. So at the end of the 5th year, if we don't pay any interest at all, we owe $7,347 on this $5,000 loan. So this is the payoff amount at the end of each year. So at the end of the first year, it's $5,400. At the end of the second year, $5,832, all the way down to $7,347 at the end of the 5th year. Now, let's look at this same loan, and we're going to repay it. But what we're going to do is we're going to pay $1,000 a year of principal. Plus, we're going to pay any interest that's due. So at the beginning of year 1, end of year 0, we're going to borrow $5,000. So that's the balance at the beginning of the year. We're going to pay $400 interest. That's 8%. So the amount we owe at the end of the year is $5,400. At the same moment in time at the end of the year, we're going to pay the $400 interest that's due and $1,000. Total payment of $1,400. 400 is interest, 1,000 is principal. So at the end of year 1, beginning of year 2, we're going to owe $4,000 because we paid the interest that was due and we've paid $1,000 principal. So now the interest on $4,000 is 8%. 8% times 4,000 is $320. We go through this same exercise. We have a smaller amount of interest due in year 2. Why? Because the loan balance is smaller. And so we're going to, this $1,000 is going to be the same for each year. That's the amount we borrowed. We're paying down the amount we borrowed, but the total payment at the end of year 2 is $1,320. Now our balance at the end of year 2, beginning of year 3 is $3,000, all the way down to year 5. So if we look at our total payments, we're going to make $1,200 in interest payments and $5,000 in principal payments, a total payment amount of $6,200. So this is a constant principal payment loan. Typically, most loans require interest payments. They may or may not require principal payments. So this is plan 1, repaying $5,000. Plan 2, we're only going to pay interest only. This is like a corporate loan. So I did loans like this, but for Union Oil, but they were typically $100 to $200 million of borrowings we would do. We would only pay interest periodically. We tended to pay it semi-annually, but for purposes of this example, it's going to be annual. And so we're going to borrow $5,000. We're going to pay interest only every year and then at the end of the 5th year, we're going to pay all the principal back. We're going to pay the $5,000 back. So every year we're going to pay $400, so our interest is going to be constant. All right, because we're paying interest, there's no interest on interest. Then at the end of the 5th year, we're going to pay the $400 and the $5,000 that we borrowed. So we have principal repayment of $5,000, interest payment of $2,000, total payment of $7,000. Notice that this total payment is different than this total payment here where we made interim principal payments. Okay, this is plan 2. Plan 3, we're going to make constant annual payments. And I'm going to tell you now that the constant annual payments are $1,252.28. In a couple weeks, maybe next week, I'm going to show you how to come up with that $1,252.28. But if you built an Excel model doing this, you would find that if you pay $1,252.28, that's what's known. The interest payment is calculated as 8% on the amount that's borrowed. Therefore, the difference, this column here, the second one from the right, is the difference between the column on the right, the total payment column, and the interest payment column. So this is a given, this is known, this is calculated, the interest payment is calculated based on the balance at the beginning of the year. And we back into what the principal payment is. But at the end of 5 years, if you add up these principal payments, they add up to $5,000. Now, they have to pay off this loan. And what I haven't told you is how to calculate the $1,252.28. But notice here that we're paying increasing principal amounts. We're still repaying the $5,000. The total interest is $1,261.41, and the total payments are $62.41. Contrasted with $7,000 if we make no principal payments, $6,200 if we make constant principal payments. So method 1 is very similar to method 3 in terms of total payments, because these payments are very close to $1,000 each. I would encourage you to build these tables and build the relationships in the tables. I think there's a homework problem that actually asks you to do it with one of these and to build one of these, this particular plan 3. Now let's look at plan 4. Plan 4 is like the example prior to this, where we're not going to pay anything until the 5th year. So therefore, our interest component increases each year because we're paying interest on the interest. And we pay back the $5,000 at the end of the 5th year. We pay back all the accrued interest, years 1 through 5. At the end of the 5th year, our total payments are $7,300.64. Now, we have 4 repayment plans. The differences are the repayment structure. The differences are the repayment structure, the different amounts of principal at different times in the total payment amount. Similarities is all interest charges are calculated at 8% and all repaid a $5,000 loan in 5 years. So this is what equivalence is. If a company thinks 8% is a reasonable interest rate, it would be indifferent between any of these 4 repayment plans. Each repayment plan is equivalent to another. Now, a bank, in theory, would be the same way. If their interest rate was 8% for 5 years, they would be indifferent to lending that $5,000 to a company with any one of those 4 repayment plans. And so what that does is this gets into the timing of the cash flows. Equivalence makes the different repayment plans equal. The most important thing is it's at 8%. So there's a given interest rate that makes equivalence possible. And so what can we do with this? By using equivalence, we can convert cash flows at different points in the future to a common reference point. What that allows us to do is to compare projects that have differing cash flows. And fundamentally, equivalence depends on interest rate. Now I'm going to stop right now and I'm going to pick up with the second part of week 3. But I think this is a very new concept. You may want to review it a couple times and actually go in and put an Excel worksheet together that does those 4 types of loans to show that, demonstrate it to yourself that those things are all equivalent.